So for the next little while, we're going to be taking a look at something called chemical kinetics, which is really nothing more than the study of reaction rates. So let's get some basic information about that first. First of all, we want to understand what kinetics are. Okay? As a reaction occurs, two things are going to happen. The concentration of reactants is going to go down as they get used up, and the concentration of products is going to increase. Now this takes some time, right? Depending on the reaction, it may take a very large amount of time, or it may be a very small amount of time. What we're interested in is how fast these changes happen. That's what kinetics, chemical kinetics is. It's a measurement of how fast reactions occur. So, if these little molecules are NO2 molecules over here in panel A, eventually over some amount of time, the NO2 molecules are going to start to break down. And you're going to see that two of them will each release an oxygen atom to become O2, and you'll have two molecules of NO. And eventually, that'll continue to happen over the course of all of the reactants until you reach products. Okay, and depending on how vigorous this reaction is, it may happen very quickly or it may not happen very fast at all. So we're going to be interested in what we call reaction rates. A reaction rate is a change in concentration of a reactant or a product per unit of time. Sometimes we measure the time of a reaction in seconds because it's really fast, sometimes in minutes, sometimes in hours. Depends on how quickly the reaction observably changes. Okay? The rate can be positive or negative depending on whether or not you're working with a reactant or a product. If you think about it, since the concentration of reactants is decreasing, the rate could be expressed as a negative rate, right? The rate of reaction is negative because the amount of reactants, if you're looking at how a reactant's concentration is changing, it's becoming, there's becoming less of it, so it's becoming more negative. But a product is being produced, and so its concentration is increasing over time, so the rate would be positive, okay? Typically, if we have a reactant rate that we're looking at, we'll just change it to a positive rate, just so that we can talk about rates in terms of change in concentration over change in time, and that's really what we're working with. Okay, reaction rate is the change in concentration over change in time, and so if you have a concentration of some reactant or some product A at one time and at another time, you can subtract the two, and then subtract the two times, and you have the rate, delta concentration of A over delta T. Now you'll notice in this figure over here we have brackets, and brackets in chemistry represent the term concentration, molarity usually. So here's an example of some data that was taken for reaction of a decomposition of NO2 into NO and O2. Okay, at various times, the concentration in moles per liter was measured. So you'll see at time is 0. In other words, right when we start this reaction, there's 0.01 moles per liter of NO2, but no NO or O2 yet. But as you go down through, as time increases, the amount of NO starts to increase and the amount of O2 starts to increase. Likewise, the amount of NO2 starts to decrease. So this is some data that we could perhaps measure for this reaction. Okay, so the reaction rate for NO2, the average rate of change in NO2, is going to be negative, so we put a negative sign in front of it. When we take the change in NO2 versus the change in temperature, time rather, if we're looking at the first 50 seconds, then it's the difference of NO2 at T50 and NO2 at T0, and then 50 seconds minus 0 seconds. So 0.00079 moles per liter minus 0.0100 moles per liter divided by 50 seconds gives us a rate of, and since we're looking at a reactant which is going down in concentration, we just put a negative sign in front of it to make the rate positive. So our rate is 4.2 times 10 to the minus fifth, and then it's moles per liter seconds. It's one way to look at it, or since moles per liter is molarity, you can have it molarity over seconds, capital M over seconds, okay? Or you can have it molarity times seconds to the minus 1, or you can have it moles times liters to the minus 1, seconds to the minus 1. There's a number of ways of representing that unit. Essentially, it's molarity, which is concentration, and seconds, which is time, change in concentration over change in time. So the reaction rate, how fast a reaction goes, decreases as time goes on. That has a lot to do with the fact that as reactants react, there's fewer of them to interact with one another, and so the likelihood of reactants coming in contact with each other to react to form products becomes less and less as you get fewer and fewer molecules of your reactants. So we tend to look at average rate over a particular period of time. Okay, but we can look at something called an instantaneous rate. An instantaneous rate is the rate of the reaction at a specific time. Since we know that overall the reaction rate decreases, we might be interested in saying, well, what is the reaction rate at this time right here, right at this particular time? And the way we're going to do that is we're going to need to graph some data, and we're going to need to calculate the slope of a tangent line to the curve of that data at that particular time. Here's what it looks like. Okay, so here's a reaction graph for how the concentration of NO2 is changing. This green line here, it's decreasing, and how the concentrations of NO and O2 are changing as we move upwards. Right, they're increasing as we go through time. So time is on the x-axis and concentration is on the y-axis. And so this is what it would look like if we were to graph that data. Over time, what happens to the concentrations of NO2 and NO and O2. NO2 is dropping, O2 and NO are increasing. Let's say that we want to find the instantaneous rate at 100 seconds. So depending on which reactant or product we're talking about, we're going to draw a straight line that only touches the curve at x equals 100, at our 100 seconds. Okay, and then we're going to find the slope of that tangent line. So if we're finding, for example, the instantaneous rate of change of NO2, then we have to find the tangent to the green, to the curve, at 100, and then find the slope of that line. If we're looking for the change in concentration, the rate of change in concentration of NO, then we would look at the NO at 100 and vice versa, O2. Okay, so we've got three different things going on here, depending on which one we want to take a look at. So the instantaneous rate then, slope, is delta y over delta x, and since y was concentration of NO2 and x is time, slope is equal to delta NO2 concentration over delta t, which means we know that the rate is equal to negative concentration NO2 over delta t, because it's a reactant, so put a negative sign in front, which means basically that the rate of the reaction is equal to the opposite of the slope. Okay, that's the rate of this reaction for NO2 at 100 seconds. So if we use values from the graph, our negative 0.0026 moles per liter over 110 seconds, that's 2.4 times 10 to the minus fifth moles per liter second. Okay, that would be our instantaneous rate at 110 seconds, not 100 seconds, 110 seconds. Now, we can do the same thing in terms of products. You don't have to do a calculation every single time. If you know the rate of a reaction with respect to a reactant, you can just use basic stoichiometry to figure out the rates of product production, the rate of product appearance, we'd say. How fast is the product appearing? We just use the coefficients, okay? In the equation, NO2 to NO plus O2, it's 2NO2 goes to 2NO plus O2. NO2 and NO have the same coefficient, so that means the rate that NO2 is being used up is the same as the rate that NO is being created, because it's a 1-to-1 mole ratio. For every mole of NO2 that goes away, we get 1 mole of NO produced. But because of oxygen is a coefficient of 1, that means that oxygen is created half as fast as NO, right? So we can represent that like this. If our rate of production of NO is 8.6 times 10 to the minus 6 liter seconds, then we use the mole ratio, 1 mole of O2 to 2 moles of NO, and we get 4.3 times 10 to the minus 6 moles of O2 per liter second. So the rate is half as fast for the production of O2, because for every 1 mole of NO that's produced, you only produce half a mole of O2. You need 2 moles of NO to produce a full mole of O2, so the rate is half as fast. Okay, so you can always use the coefficients to figure this out. So taking this into account, here's the example I'd like you to try. If the rate of creation of O2 at a particular time is 4.0 times 10 to the minus third moles per liter second, what's the rate of disappearance of NO2 at that time? And then what's the rate of creation of NO at that time? So go ahead and shut off the video, try it, and we'll take a look at it in class.